Welcome you all. Today we are going to discuss one more problem in a gas turbine. The question is, in a gas turbine, the compressor is driven by the high pressure turbine. The exhaust gas from the high pressure turbine goes to a lower pressure turbine which runs the load. The airflow rate is 20 kg per second and the minimum and maximum temperature are respectively 300 Kelvin and 1000 Kelvin. The compressor pressure ratio is 4. Calculate the pressure ratio of the low pressure turbine and the temperature of exhaust gases from the unit. The compressor and turbine are isentropic. Cp of air and exhaust gases is equal to 1 kilojoule per kg Kelvin and gamma is equal to 1.4. Neglect the mass of the feed. They given the mass flow rate of air is equal to 20 kg per second. Minimum temperature 300 Kelvin. Maximum temperature 1000 Kelvin. The pressure ratio in the compressor P2 by P1 is equal to 4. Cp of air and the exhaust gases 1 kilojoule per kg Kelvin. Gamma is equal to 1.4. So that is T1 is equal to 300 Kelvin and T3 is equal to 1000 Kelvin. Assume that the compression and expansion are isentropic. From temperature entropy diagram, 3 pressure levels are there. Isentropic compression from 1 to 2. Then in the combustion chamber 3. High pressure turbine 3 to 4. Then the low pressure turbine 4 to 5. We know that this is the inlet temperature to the compressor and the compressor to a state point 2. Combustion takes place from the combustion chamber 2 to 3. Then high pressure turbine 3 to 4. Low pressure turbine 4 to 5. Now find 1. The pressure ratio of low pressure turbine, that is P4 by P5. Second, the temperature of gases leaving from the unit, that is T5. So they are asking pressure ratio of low pressure turbine. So that is P4 by P5. That we can be obtained from P4 by T5 is equal to P4 by P5 whole to the power gamma minus 1 by gamma. Then T5 is equal to T4 over P4 by P5 whole to the power gamma minus 1 by gamma. So we have to find out first P4 by P5. Isentropic compression process 1 to 2. We know that isentropic relation, that is T2 by T1 is equal to T2 by P1 whole to the power gamma minus 1 by gamma. T2 is equal to T1 into P2 by P1 whole to the power gamma minus 1 by gamma. T1 is equal to 300 Kelvin. 300 multiplied by 4 whole to the power 0.4 over 1.4, that is equal to 445.79 Kelvin. And we know that work of compressor is equal to work of high pressure turbine multiplied by mechanical efficiency. Assume 100% mechanical efficiency. This work of turbine is equal to mass of air into Cp of air into T2 minus T1. Mass of the air plus mass of the fuel into T3 minus T4. Then so mass of the fuel is neglected, so that T2 minus T1 is equal to T3 minus T4. Cp of air and gas equal to 1. That is 445.79 minus 300 is equal to 1000 minus T4. We get T4 is equal to 854.20 Kelvin. Now high pressure turbine T3 by T4 is equal to P3 by P4 whole to the power gamma minus 1 by gamma. Then P3 by P4 is equal to T3 by T4 whole to the power gamma minus 1 by gamma. That is equal to P3 by P4 is equal to T3 by T4 whole to the power gamma by gamma minus 1. That is equal to 1000 over 854.2 whole to the power 1.4 divided by 0.4. We get P3 by P4 is equal to 1.736. We can write this left hand side, P3 by P4 is equal to P3 by P5 multiplied by P5 over P4, that is equal to 1.736. P3 by P5, that is equal to P3 by P5 is equal to P2 by P1 and P5 by P4 is equal to 1.736. P2 by P1 is equal to 4 multiplied by P5 by P4 is equal to 1.736. We get P4 by P5 is equal to 2.304, answer 1. The second one is, in that low pressure turbine, we know that T4 by T5 is equal to P4 by P5 whole to the power gamma minus 1 by gamma. T5 is equal to P4 over P4 by P5 whole to the power gamma minus 1 by gamma. That is T5 is equal to T4 854.20 over 2.304 whole to the power 0.4 divided by 1.4. T5 is equal to 672.9 Kelvin, answer 2. So this pressure ratio of low pressure turbine is equal to 2.304 and the temperature leaving of the unit is equal to 672.9, that is equal to 673 Kelvin.
Subscribe to our channel, like if you're satisfied, and share because it may be useful to someone.